Now let's continue with mathematical induction. So let's work on proving divisibility stuff. So when we have induction, this extends just beyond going in summation formulas. We can use this with some properties in number theory, among them things that we can do with divisibility. So statements of the sort of to prove that D divide f of n for all n bigger than a are done by using induction. So here the basic step is going to be that we show that the number D divides f of a by direct computation. Then we assume we start by the inductive step next, which is assuming that D divides f of k for a certain k. And this means that it's just an integer such that f of k is going to be equals d times m. And then we're going to show that d divides f of k plus 1. We're going to write f of k plus 1 in terms of f of k plus additional terms. And we're going to factor out to show that f of k plus 1 is equals d times some integer. So let's see an example of that. For all integers n bigger than 0, we have that 7 to the n minus 1 is divisible by 6. So first, let's state what p of n is. P of n will be 6 divides 7 to the n minus 1. Then the basic step is to show that for 0, this is true. Now, in 0, we have 7 to the 0 minus 1, which is just 1 minus 1, which is 0. And so by default, since we can see 0 as 6 times 0, we have, 6 divided 0. And hence, P of 0 is true. Now, the inductive hypothesis. Suppose that 6 divided 7 to the k minus 1 for some k bigger than 0. By definition of divisibility, is going to exist in number m, integer, such that 7 to the k minus 1 is equals 6m. Now, we want to show that 6 divided 7 to the k plus 1 minus 1. So first, let's check 7 to the k plus 1 minus 1 and put this in terms of something that we can manipulate. So 7 to the k plus 1 minus 1 is equals to 7 times 7 to the k minus 1. Now, this is something here that we cannot yet do anything, since this 7 is in here working. However, we can break apart adding and subtracting 7. So if we add and subtract 7, notice what happens. We subtract 7 and we add 7, and then we're going to factor out the 7. And so if we factor out the 7, we get 7 to the k minus 1, and then this 7 minus 1 becomes a 6. Now, by inductive hypothesis, 7 to the k minus 1 is going to be equals to some 6m for some integer m. So now this part is going to transform into 7 times 6m plus 6. Or we can see the entire thing as 42m plus 6, which I can factor as 6 out of it and it becomes 6 times 7m plus 1. So now notice then we just find out that 7 to the k minus plus 1 minus 1 is a multiple of 6. And since here this 7m plus 1 is an integer, by m being an integer, 7 being an integer, and 1 being an integer, then we just proved that 7 power to the k plus 1 minus 1 is 6 times some integer. Hence, 6 is going to divide 7 to the k plus 1 minus 1, and we just prove the inductive hypothesis. And so by mathematical induction, we're going to have that for all n, this is true. 6 divided 7 to the n minus 1. Now let's talk about proving inequalities, which is the other type of thing that we can do with also induction. So for proving inequalities, we want to prove that f of n is less than g of n, or you can go with less or equal, or bigger than, or bigger or equal for n bigger than a. The idea is that we verify that this is true for an n equals a, and then we go with the inductive hypothesis. We assume that f of k is less than g of k, and then we're going to prove that f of k plus 1 is less than g of k plus 1. The strategy is start with f of k plus 1, express it in terms of f of k, use the inductive hypothesis, and show that our result is going to be less than g of k plus 1. Often, you're going to need an auxiliary inequality that uses that k is bigger than a. Let's see an example of that. So for all integers n bigger than 3, we have that 2n plus 1 is less than 2 to the n. So the p of n is going to be 2 of n plus 1 less than 2 to the n. Then the basic step is proving it for 3, since 3 is the initial value that we're using here. And so notice 2 times 3 plus 1 is just 6. And so 6 plus 1, 7. And that's going to be less than 2 to the 3, which is 8, by the way. So we can see that 7 is less than 8, and so p of 3 is true. We have the basic step. Now, let's go for the inductive hypothesis. We suppose that for some k bigger than 3, we have that 2k plus 1 is less than 2 to the k. Now, our goal is to show that 2k plus 1 is going to be less than 2 power to the k plus 1, which is, this will be the k plus 1 step. If we check what this means really that 2k plus 3 is less than 2 to the k plus 1. Now, let's start with the left side. So 2k plus 1 is just going to be 2k plus 3. But that also can be seen as 2k plus 1 plus 2, right? Now, by inductive hypothesis, 2k plus 1 is just going to be less than 2 to the k. So we have that this piece is less than 2 to the k, and this is 2. So overall, we have the 2k plus 1 is less than 2 to the k plus 2. Then, from here, notice then 2 to the k plus 2 is going to be less or equal to 2 to the k plus 1, or we want to prove that. So since 2 to the k plus 1 is 2 times 2 to the k, then we can just check that this will become 2 to the k plus 2 less than 2 times 2 to the k. So simplifying this, we'll just simply say that 2 gotta be less than 2 to the k. Since k is bigger than 3, we're going to have that 2 to the k is bigger than 2 to the 3, which is 8, and that's going to be bigger than 2. So we can say, okay, yeah, 2 to the k is bigger than 2. Okay? So if that is unclear, notice that, once again, we want to prove this step. And so what we're doing is, this is twice 2 to the k. So it's like each of the pieces, 2 to the k plus 2, is less than 2 to the k plus 2 to the k. So 2 to the k gets canceled, and I just need to prove that 2 is less than 2 to the k. But I just proved that because k is bigger than 3. And then we're going to have that 2 to the k bigger than 2 to the 3, which is 8 that's bigger than 2. So hence, we have that 2k plus 1 is less than 2 to the k plus 2, which is less than twice 2 to the k, which is 2k plus 1. So p of k plus 1 will be true here. And once again, I just want to reiterate this small step here. So let me make a brief clarification. I want to prove 2 to the k plus 2 is less than 2 to the k plus 1. Right? This is what I want to prove. But I can start from the fact that k is bigger than 3, right? So if k is bigger than 3, 2 to the k is bigger than 2 to the 3. This hypothesis leads me to this. And so this is 8, right? And a is bigger than 2. So in conclusion, if k is bigger than 3, 2 to the k is always going to be bigger than 2, right? So, in particular, then, if I add 2 to the k, so 2 to the k plus 2 to the k is going to be bigger than 2 plus 2 to the k, right? But now notice that this is just twice 2 to the k, and this is 2 to the k plus 1. And so with this, I have that 2 to the k plus 1 is going to be bigger than 2 plus 2 to the k, which is what I wanted. Okay? And so that proves here my k plus 1 step. And so, by conclusion, 2 to the n plus 1 is going to be less than 2 to the n for all n bigger than 3. Now, another example. Something similar. 1 plus 3n is less than 4 to the n if n is bigger than 2. Once again, basic step. We prove that for 2 is true. For 2, the property is going to be true. So 1 plus 3 times 2 is just going to be 7. And that's going to be less than 4 squared, which is 16. So we have that the basic step is true. Now, the inductive hypothesis, we have that 1 plus 3k is less than 4 to the k. And so our goal is to show that 1 plus 3k plus 1 is less than 4k plus 1. This here is equivalent to 4 plus 3k less than 4k plus 1. The idea is the same as we just did. Notice that I want to prove this step. We have 1 plus 3k plus 1 is just 1 plus 3k plus 3. So we can see that by inductive step, this is going to be less than 4 to the k. So we have that this is less than 4 to the k plus 3. Now, I want to prove that 4k plus 3 is less than 4k plus 1. And we use the same idea as we did before. Notice that because we have that n is bigger than 2, then 4 to the n is going to be bigger than 4 to the 2. Okay? Or by simplification, since k bigger than 2, 4 to the k bigger than 16, but that's bigger than 1. We're adding 1 4 to the k more. Okay? So we're from here, we add 4 to the k on both sides. That gives me 4 to the k. And here will give me 4 to the k plus 3. Now, but remember, then that will just prove what we want. So here I'm going a little bit backwards, but we're really starting from this hypothesis. In k is bigger than 2, 4k is bigger than 4 squared, that's bigger than 16, bigger than 1. And then from here, we multiply by 3 both sides, and then we add 4 to the k on both sides, and we get this inequality. And because this is 4 to the k plus 1, then we just proved this. And so hence, we get that 1 plus 3k plus 1 will be less than 4k plus 1. And so now, by principle of mathematical induction, that's going to give me that this works for all n. Now, in summary, the key techniques is for divisibility of proofs, we need to express f of k plus 1 in terms of f of k. Use the hypothesis that f of k is divisible by d. Factor out the entire expression and verify that the factor is an integer. For the inequality proof, you start with the more complex side, usually the left side. Express in terms of the key version, apply the inductive hypothesis, and show that the results satisfy the inequality for k plus 1. We often are going to need the fact that k is bigger than some number, that is our starting hypothesis. So common manipulations are part of the n-subtract powers. So for things like ak plus 1 is a times a to the k, and then we can add or subtract things like, for example, here we just added and subtracted a to the k to get some manipulations in there. Common mistakes include that you start with the wrong value. Once again, not expressing the k plus 1 term in terms of of the k term for proving. Forgetting to factor out divisors on the division proofs. The change in directions for the inequalities. So you gotta be careful with those and not verifying that you're using auxiliary inequalities for the inequalities that you need to find. So in summary, we just show that induction works for many type of statements, not just summation formula, but you can use divisibility, inequalities. The divisibility strategy is expressing the k plus 1 terms in terms of the f of k and factor out the divisor d. And the inequality strategy is always about chaining inequalities, where the initial constraint is going to help me out, facilitate the other inequalities. Always check that you're doing the initial step, that you're using the inductive hypothesis on your proof, and then all the algebraic steps are correct. Okay, next we're going to see recursive sequences, but make sure to take a look at the videos with the examples for these sections, where I'm going to go in more detail about more exercises in divisibility and inequalities.